All right, guys, this is part B for chapter 6, which is Hess's law, and probably one of the more difficult types of calculation for enthalpy, um, because it's not a similar equation like MCAT and using a calorimetry. This is using known values of enthalpy and taking different pathways to get to the final reaction. So this is probably the harder of the three methods, and make sure you follow along the steps and rewind if you need to. So the first thing understanding is in a reaction you have reactants, obviously. So here's the combustion of methane, and it has energy, and that energy is built up in their bonds. So the carbon-hydrogen bond has an energy that you need, and the oxygen-oxygen bond is energy as well. Right now it's potential because nothing's happening. There's no breaking of the bonds yet or forming new bonds. So for every reaction possible, you have to break apart the reactants. So what happens is that we need to take energy and break apart these carbon-hydrogen bonds and break apart the oxygen-oxygen bond for them to make new products. So that requires activation. So that's called the activation energy. So the energy needed to break all the bonds and create chaos is called the activation energy. Activates the reaction. So you can't make anything until all the bonds are broken, or some of the bonds are broken. Okay, so that takes energy. So you can see why it goes up in the graph. Now you have all this chaos of atoms, and what has to happen is you want to become stable. So they're going to form new bonds, and that's where you get carbon dioxide and water forming. Now that takes not, it releases energy. So that's why it goes down. So when you make new bonds, it releases energy, and now you have a stable product. That's why it levels off at the end. You have water and carbon dioxide. So that energy change, okay, between the activation and the release is the enthalpy of the reaction, the overall energy of the reaction. How much energy it takes to break and how much energy it releases tells you how much the enthalpy of the reaction. In this case, it releases energy because the energy releasing is more than the energy broken, so it's exothermic. So you have two types of energies, exothermic and endothermic. So you can see this is an energy profile that we're basically doing. The energy is going to go up at both times because it takes energy to break the bonds. And then the release of energy depends if it's exo or endothermic. So the release, if it's greater than the activation energy, it's exothermic. So the energy is going to be negative, okay, because you're taking a small number minus a big number, you get a negative value. Where in endothermic, the energy is greater than zero, it's positive because the energy releasing is less than the energy breaking, the activation energy. So you can see delta H on both cases. If it's negative, it's exothermic. If it's positive, it's endothermic. So this is what we've done so far. We calculate enthalpy through experimentation using a calorimetry and using MCAT and divide by the moles of your reactant. So very similar to what we did with magnesium and hydrochloric acid. That's experimentation. So we'll cross that out. Now we're going to do number 2, which is the heat of formation reactions, or Hess's law, basically using these reactions to determine the overall reaction, enthalpy of reaction in the experiment or the reaction itself. Okay, and then later we'll do bond energy. So we're probably going to switch over cameras. All right, so this is going to be how we're going to show. You can see how we're doing on the screen, and then if I need to be in the camera or not, we'll see. So Hess's law is a summation of enthalpy of reactions, is independent of the pathway, meaning it doesn't really care how it's getting to the final product. It can get there very quickly. It can get there with a lot of bumps and ups and downs of different reactions. But overall, you'll have the same enthalpy of reaction. So think about if you're going to get to Tampa. Multiple ways to get to Tampa. There's multiple back roads. The quickest is to I-75. But you are still going to get to Tampa. The overall energy should still be the same, but it's different ways to get there. So this is what Hess's law is basically saying. We have two reactions. We have magnesium carbonate with hydrochloric acid and MgO with hydrochloric acid. And they make different products. They both make MgCl2 and make water, but the first reaction makes CO2. So the question is, which species, or what pen. All right. Which species, basically what compounds you have in reaction 1 and reaction 2 are not in the reaction below. So what is not in the final reaction? So this is basically our final reaction. What species get consumed and produced through the whole thing so they don't show up in the final reaction. So we look at, first thing we have magnesium carbonate. We don't have hydrochloric acid, so that one's going to get rid of. We don't have MgCl2. We have CO2, and we don't have water in the final reaction. Take a second reaction, we have MgO right here. We do not have hydrochloric acid, we do not have water, and we do not have magnesium chloride. So basically, Hess's law is showing that these species are independent to the final reaction, meaning they're going to get produced and consumed. So the energy they needed to get produced and the energy they do need to get consumed are going to wash out. Okay, so we care about the final reaction. All right. So let's go understanding how we calculate enthalpy. So this is the reaction we did with the calorimetry. We took magnesium, we added hydrochloric acid, and we made hydrogen gas and a solution of magnesium chloride. So we're going to use the graphical representation, the profile. Okay, that's this graph. You have the pathway, and you have energy. Okay, and basically you're starting at an arbitrary amount. Okay, in this case we have magnesium plus 2, what's that? HCl. Okay. Now, if you look at the two reactions that we have, formation reactions, they're formation because they're both 1 mole of product, and they're both made from their common elements, or the basic elements. We basically have, the formation of magnesium is 0. We can't form something that's an element, okay? But we do need the hydrochloric acid. So if we want to break apart hydrochloric acid, we need to know how much energy required to break apart 2 moles of energy, because we need to get everything into the bonds broken. Okay, so it takes that much energy to form hydrochloric acid to make it. So that means if we want to figure out how much we need to break it, it's the opposite. It's positive. Always going to be endothermic because you always need energy to break bonds. So we need this energy here, right here, activation energy. That's going to be how much it needs to break hydrochloric acid. So it's going to be a positive 168. Why 168? Because we have 2 moles of hydrochloric acid. And this is for 1 mole of hydrochloric acid. So we have to multiply this by 2 to get 168. Okay? Now, once the reaction occurs, it's going to go down. So how much is it going to go down? We're going to form magnesium chloride. Right? Again, H2 is elemental, so it's going to be 0. So all we care about is forming MgCl2. We also care about that we're making hydrogen gas, but hydrogen's elemental, so it's not going to have any formation energy. So this energy here, we're going to change colors. Let's do yellow. Energy here is going to be negative 640.7 kilojoules per mole. I should say that for 168. Okay. And then we need a calculator because the difference here, the amount of energy here and here, is our delta H. Okay. Let's go to weight. So delta H is going to be the difference between these two values. So negative 640.7 plus 168. And we get negative 472, well, 72.7 negative, which makes sense because we know that it's exothermic because the temperature went up when we did this reaction. So this would be a known value. So the experiment is experimental. So you're not going to get that. You get close to the value if you do the experiment well, and do your calculations well, and your data collection well. But this is the known value that you should get when you mix magnesium with hydrochloric acid. Okay. All right, let's do some other more examples. Here we have the combustion of propane. Okay, and we're going to do the same setup, and we're going to start with our graph. Do red again. Energy, pathway, and an arbitrary value. This is going to be C3H8 and O2. Okay, we don't need to know about oxygen because it's elemental. Okay, so it's going to be 0. But we do need to break apart C3H8. So we're given this amount of C3H8. That's to form C3H8, propane. That's to form it. So we want to break apart, we have to switch this to a positive 124. Okay? So it takes that much energy to break apart C3H8. Then we're going to do this. Well, we should know it's going to be exothermic. Any combustion reaction is exothermic. We're going to make 3 moles of CO2 and 4 moles of water. So we look at CO2. Here it is. That's the form to make 1 mole is 393. So we're going to go with yellow. It's going to go down here. 3 moles of negative 393. Okay. The reason why it's still negative because we're forming it. Any formation reaction is negative. And 4 moles of water at 285. Okay. So that is our reactant product side. That's our red is our reactant side. We're going to add up those net numbers. So we have 3 times 393, negative 1179 kilojoules per mole. And for water, 4 times 285, negative 140 kilojoules per mole. And then for our propane, it's only 1 mole, so positive 124 kilojoules per mole. Wait, what do we get? 179 plus 124, negative 295 kilojoules per mole equals delta H. Okay, so that reaction, if you had 1 mole of propane and combust, you would make over 2,000 kilojoules of energy. Okay, if you had 1 mole. All right, so that's showing the representation of the graph, what's happening chemically. Now, using Hess's law basically is using the reaction without the formation, without the profile. So basically showing how these reactants cancel out, these species, these products and reactants cancel out to get the final reaction. So as we said before, this is the same example we had. We had HCl, HCl, water, magnesium chloride, and water. Those are the species that are not in the final reaction. That means they have to be eliminated. They have to be gone. They cancel out. So basically what Hess's law is taking these two reactions and getting the final reaction, rearranging them. So the best way to do it is always start with our reactants. Okay? So MgCO3. So you look at the reaction with MgCO3, which is the first reaction, and it's a reactant, and that's a reactant. So we don't have to do anything with reaction 1, we just have to write it out as shown. And the reason why we just write it as shown is because we wanted to keep it as a reactant. Okay? Now we look at the second reaction, MgO, that is a reactant there, but in the final reaction it's a product. So that means it has to get flipped. So everything that's a reactant will become a product, and everything a product will become a reactant. So we have H2O plus MgCl2, and we make MgO plus 2HCl. Right? So all we did is took reaction 2 and we flipped it. Let's do our basically our cancelization. Notice we have water as a reactant and water as a product. They get canceled out. We have magnesium chloride as a reactant, magnesium chloride as a product. They get canceled out. 2HCl as a reactant, 2HCl as a product. They get canceled out. So you're left with MgCO3, which is right here, MgO, which is right there, and CO2, which is right as a product. So our final reaction is exactly what we want using the two reactions to get one reaction by eliminating the species. Now, how does that work with enthalpy? Is basically these reactions that we're given, 1 and 2, have enthalpies. Every reaction has enthalpy. So when we add them all up, we get the final enthalpy of this reaction. Okay, so I'll show you that as examples here. All right. So we'll go back to our awesome magnesium reaction with hydrochloric acid. Very common reaction, is one of their favorites in ACE. And I'll show you using Hess's law instead of the graphical representation how we get the value. The graph does help. It shows you a visualization, but Hess's law is more systematic, I guess. So this is our final reaction that we want. All right, we need to get that. So we look at our two reactions. Magnesium is a reactant, magnesium is a reactant, so we want to write it as shown. Okay, make sure it's the same number of reactants, one coefficient, and magnesium chloride is one coefficient, and delta H doesn't change because we didn't change the reaction. Okay, now we look at our next reactant, HCl, and that's going to be the second reaction, but the second reaction has HCl as a product. So that means this needs to be flipped. And we have two of them, so everything here also needs to get multiplied by 2, which means this gets multiplied by 2. All right, so we take our 2HCl, we have one of these now, so 2HCl, and we're going to make H2 and Cl2, and our delta H is now positive because we flipped it. Okay, so we flip the reaction, energy flips 168 because we multiply by 2. So let's get our yellow out, cancel out some things. We can cancel out Cl2 and Cl2. Okay, and that's all thing that gets canceled. Go to our white. So Mg plus 2HCl yields MgCl2 plus H2. And our delta H is now going to be the summation of those. I should have it memorized. 7 negative 472.7 kilojoules per mole, which is the same value we got using the graph. Okay, so that's Hess's law, basically taking different reactions and rearranging them to get the final reaction and summing up the delta H's. All right, we'll take the same reaction we did with propane, and instead of using graph, we're going to use Hess's law. And I think we'll change colors a little bit. Let's go to green. So this is what we want. We want propane. So we start with propane, and that's going to be our third reaction. But since propane is a reactant, we need to flip our third reaction to make it a reactant. So C3H8 yields 3 carbon, 4H2. Delta H is positive 124. Okay, because we flipped it. You flip the reaction, you got to flip the energy. Second reaction we want, we're going to skip oxygen. We want CO2. We want 3 of them. So we have to multiply our reaction by 3. So we're going to do 3 carbons, 3 O2 yields 3 CO2. Delta H is going to be 3 times negative 393. Stays negative because we didn't flip the reaction. All right, water. Again, water is a product. Water is a product. So we want 4 of them. So this has to get multiplied by 4. We get 4H2 plus 2O2. Okay, and delta H is 4 times negative 285. All right, we're going to get some red out to cancel out. We want C3H8, 3 carbons, gone, gone. One's a reactant, one's a product. H2, 4H2, 4H2 is gone. All right, and then we add them all up. We get C3H8 plus 5O2, because 3 plus 2 is 5. 3CO2 plus 4 waters. Then we take our delta H, we add them all up. 3 times 393, 4 times 285, plus 124 is negative 2195 kilojoules per mole, which is the same value we got using the graph. Okay, so it's the same idea with the graph because we flipped the propane because it's not forming it, it's breaking apart. That's why I went to positive, and everything else was forming, so that's why they're negative. All right, let's try this one out. We want the formation of C2H6. Okay, so that's what we're trying to find. We have 3 different reactions to use, and we're going to start with carbon. It's a reactant, and here carbon is a reactant. And the first reaction is only 1 carbon, therefore we need to multiply this first reaction by 2 to get 2 carbons. So 2C plus 2O2 makes 2CO2, and delta H remains negative, but multiplied by dose. Okay. H2, again, is a reactant, and a reactant there, but we have to multiply it by 3, because we want 3 H's, H2s. So that means the enthalpy gets multiplied by 3. 3H2 plus 3 halves O2 yields 3H2O. Delta H stays negative, but multiplied by 3. Okay. Final reaction is the combustion of ethane. So C2H6 is a reactant, but we need C2H6 as a product. Okay. So we have to flip the third reaction, and it stays with 1 mole because we have 1 mole. 7 halves O2, and we have 2 CO2 plus 3 H2O. Delta H will get flipped because the reaction gets flipped. Okay, get my yellow out. What cancels and what's gone away? We need carbon, have that. CO2 through 2 CO2s, 2 CO2s. 3 waters, 3 waters. Now, oxygen is difficult because we have a fraction. 2 O2 is 4 halves. 4 plus 3 is 7 halves. Bam, gone, gone. All the oxygen's gone. And now we get 2 carbon plus 3 H2 yields C2H6, which is exactly what we need. Way up there. Okay, and we just use our math. Negative 393.5 times 2, 285.8 times 3, and plus 1559.7. We get negative 84.7 kilojoules per mole as delta H. Okay, that is how much energy it would make when you form ethane. Okay, it's the formation of ethane. So if you want to make C2H6, it would take about 85 kilojoules per mole. It would release 85 kilojoules per mole if it's negative. All right, last one. If you want to make NO2, it's not a formation reaction. It looks like it, but you have 2 moles of NO2. And we're given 3 reactions to find our delta H of that reaction. So, orange now. we need to look at our reaction. We want N2. First one has N2 and it's 1 mole, so we keep it at 1 mole. We're making ammonia here. Reaction stays the same. That means the energy stays negative because it's negative in the reaction. All right, we want O2, so that means the third reaction here has oxygen, and we need 2 of them. So what do you multiply 2 by? We have to multiply by 4, and it needs to get flipped. So we want 4H2 plus 2O2 yields 4H2O. Delta H becomes positive 4 times 174.8. Okay. That leaves us with our second reaction. We have 2NO2. We want 2NO2, so nothing is going to change. There's our 4 waters. 2NO2 plus 7H2. Delta H stays negative. We didn't flip it. And we don't have to multiply anything. All right. So I read out. This is my favorite part, canceling things out. We have 2 NH3s. We have 4 waters. We have 3 plus 4. That's 7 H2s. Boom. We have N2. We have O2. We have N. And there you go. N2 plus 2O2 makes 2NO2. And delta H will be negative 82.7 kilojoules. Okay. So it can be very difficult. Okay. But it takes a lot of organization. So you got to organize your work. Okay. And make sure everything cancels that you need to. Takes a lot of practice. And make sure you have any questions. Let me know. And we'll do more practices in class. And a little long, but that's why you have 2 days to watch this.